Welcome to today's session. In this video, we'll tackle an exciting problem from LeetCode, number 1108, defanging an IP address. This problem is beginner-friendly and a great way to practice string manipulation techniques. Let's dive in and explore the solution step by step. In this problem, we are tasked with creating a defanged version of a given IPv4 address. An IPv4 address consists of 4 numeric segments separated by periods, and the goal is to replace every period in the address with the string dot. This transformation is known as defanging. The input to the problem is a string representing a valid IPv4 address, which contains only digits and periods, with no leading or trailing periods. The output should be a new string where all periods in the input have been replaced as described. For example, if the input is address equals 1.1.1.1, we are expected to return the defanged address as the output. The output for the input 1.1.1.1 would be 1.1.1.1. This is because each period in the input string has been replaced with dot. Another example is the input address equals 255.100.50.0, where the output would be 255.100.50.0. Similarly, the transformation involves replacing each period with dot, resulting in the defanged version of the address. So, for any valid IPv4 input, we simply follow this process for each period in the string to produce the correct output. Another example is the input 192.168.0.1. Here, the defanged version of the address would be 192.168.0.1. Again, this follows the same rule of replacing every period with dot. The problem also specifies a few constraints. The input is always a valid IPv4 address, meaning it contains exactly 3 periods, and each segment is a number between 0 and 255 inclusive. The string is between 7 and 15 characters long, and there are no leading zeros in any segment. For instance, 1 foot is not a valid segment. Some additional edge cases to consider include the smallest valid IPv4 address, 0.0.0.0, which would transform to 0.0.0.0, and the largest valid address, 255.255.255.255, which would become 255. We can also have inputs with varying segment lengths, such as 10.0.123.4, which transforms to 10.0.123.4. Finally, in cases where each segment is a single digit, like 1.2.3.4, the output would be 1.2.3.4. These examples demonstrate the versatility of the solution across different forms of valid input. To approach this problem, we considered several strategies. The first is the brute force approach, which involves iterating through the string one character at a time. As we go, whenever a period, or dot, is encountered, we append to a new result string. For all other characters, we simply copy them over as is. This approach is straightforward and easy to understand, making it a good starting point. However, there's a trade-off. While it's simple to implement and works well for small strings, it's not the most efficient. This is because in languages like Python, strings are immutable, meaning every time we modify the string, a new one is created. This repeated concatenation can lead to a time complexity of n squared, in the worst case. Next, there's an alternative approach using Python's built-in strreplace method. With this method, we directly replace all occurrences of the period with dot in a single step. This method is highly optimized for string operations, eliminating the need for manual iteration. It processes the string in n time, which is far more efficient than the brute force approach. However, it may feel less intuitive to beginners who aren't yet familiar with built-in methods. Building on that, this strreplace method has clear advantages. It's cleaner, more readable, and optimized for performance. But for those new to programming, the abstraction might make it harder to understand how it's working under the hood. Another option we considered is using regular expressions, or regex. With regex, we can search for all periods in the string and replace them with using a substitution function. The strength of regex lies in its flexibility. It's a powerful tool for pattern matching and can handle far more complex tasks than this one. However, while regex is versatile, it's overkill for this particular problem. It introduces unnecessary complexity and might even be slower than strreplace for small strings due to its additional processing overhead. Considering all these options, the strreplace method emerges as the most practical choice. It's efficient, simple, and well suited to the problem at hand. Here's how we apply the chosen strategy using the strreplace method. First, we call the replace method on the input string, passing in two arguments. The first argument is the character we want to replace, which is the period, and the second argument is the string we want to replace it with, which is dot. The method then processes the string in a single pass, replacing all occurrences of the period with dot. Finally, we return the result of this operation. Let's look at the Python code implementation. It's concise and to the point. We define a class solution and a method definiPattern that takes the input string address. Within the method, we simply return the result of address.replace. This implementation highlights how the replace method simplifies the task, achieving the desired transformation in just a single line of code. This problem provides a great example of how built-in methods can simplify and optimize solutions. The key takeaway is recognizing that the strreplace method is both efficient and intuitive for this kind of task. The main insight, or aha moment, comes from realizing that this method performs the replacement directly and in a single step, avoiding the inefficiencies of manual string concatenation and the unnecessary complexity of regex. Comparing the approaches, the brute force method struggles with performance due to its n² time complexity, while regex, the flexible, is overcomplicated for such a straightforward problem. The strreplace method strikes the perfect balance, offering simplicity, clarity, and efficiency. Ultimately, it's the optimal choice for defanging an IP address, making the solution not only effective but also easy to understand and implement. To solve the problem of defanging an IP address, we start by understanding the task. We are given an IPv4 address as a string, such as 192.168.0.1, and our goal is to return a modified version where every period, represented by the dot character, is replaced with dot. This transformation ensures the IP address is represented in a defanged format. The algorithm begins by validating the input. We need to ensure that the input string is not empty, as an empty input could lead to undefined behavior. If the input is empty, we can immediately return an error or an empty string. Next, we initialize an empty string called result. This will serve as our storage for the transformed version of the IP address as we process each character. Finally, we iterate through the input string character by character. For each character, we check whether it is a period. If it is, we append to our result string. These steps lay the foundation for transforming the IP address into its defanged form. When iterating through the characters of the IP address, if the character is not a period, we simply append the character to the result string as it is. This ensures that all non-period characters remain unchanged in the output. Once the loop has processed all the characters in the input string, the result string will contain the fully defanged IP address. For example, given the input 192.168.0.1, we start with an empty result string and append each character step by step. First, 1 is added, resulting in 1, then 9 is added, giving 19, and so on. When a period is encountered, we append dot instead. By the end of the loop, the result will be 192.168.0.1. This final string is then returned as the output. This approach guarantees that every period is replaced with while all other characters are preserved, ensuring the desired transformation. Iterating character by character allows us to precisely identify and replace only the periods in the input string without affecting other characters. This method ensures accuracy and simplicity in transforming the IP address. By using string concatenation to build the result, we can efficiently construct the defanged version for small-scale inputs like an IPv4 address. However, for larger datasets, it's worth noting that strings in Python are immutable, meaning each concatenation creates a new string in memory. In those cases, appending to a list and joining the elements at the end could be more optimal. Several edge cases are also considered in this solution. If the input string is empty, we simply return an empty output. If the input contains no periods, the output remains unchanged. For example, 1234 would return as 1234. Finally, if the input contains only periods, like, each period is replaced correctly, resulting in dot. These considerations help ensure the algorithm handles a wide range of input scenarios effectively. Analyzing the algorithm's complexity, we find that the time complexity is O(n), where n is the length of the input string. This is because we traverse the string exactly once, processing each character in constant time. The space complexity is also O(n), as we construct the output string, which requires space proportional to the size of the input. Additionally, the replacements add extra characters, but this is still proportional to n. For optimization, while the current approach of string concatenation works well for small inputs, we could use a list-based approach for larger strings. By appending each transformed segment to a list and joining the list elements into a single string at the end, we avoid the overhead associated with Python's immutable strings during concatenation. This optimization is particularly useful when dealing with massive datasets. The provided Python implementation demonstrates these concepts clearly, showing how to iterate through each character, check for periods, and construct the defanged IP address in an efficient manner. Here is the complete implementation of the solution. The function defang_IP_address takes an input string, which represents the IPv4 address to be defanged. It initializes an empty result string and iterates through each character of the input. If the character is a period, is appended to the result, otherwise, the character itself is appended. After processing all characters, the result string, which now contains the defanged IP address, is returned. For example, calling the function with the input 192.168.0.1 returns 192.168.0.1 as expected. This implementation is straightforward and effectively handles the transformation in a way that is both clear and efficient for the given problem constraints. This implementation solves the problem of defanging an IPv4 address by replacing each dot with dot. The defang_IPattern method is defined within the solution class, which is commonly used in LeetCode problems. The function takes a single string address as input, representing a valid IPv4 address. The replace method of the string class is utilized to replace all occurrences of dot with dot. This method is efficient and directly modifies the string without requiring additional loops or memory overhead. The result is returned as the defanged IP address. This solution operates in O(n) time complexity, where n is the length of the input string, since the replace method iterates through the string once. Overall, this implementation is concise, efficient, and adheres to the problem constraints. This is the Java implementation of LeetCode problem number 1108, defanging an IP address. The logic mirrors the Python solution, where we replace every dot in the input IP address string with dot. In Java, we utilize the string.replace method to achieve this. The function takes a string as input and returns the modified string as output. The class structure is standard for LeetCode problems and adheres to Java conventions. In this problem, our goal is to define an IP address by replacing every dot, or period, with the string dot. This is often done for security purposes to prevent the IP address from being misinterpreted as an actual link. Let's start with the first example, where the input IP address is 192.168.1.1. The first step is to initialize the input, which is stored in a variable called address. Here, address is simply a string containing the IP address. Next, we use the replace method to perform the transformation. This method works by scanning the string and replacing every occurrence of a dot with dot. As it processes the string, the first dot is replaced, resulting in 192.168.1.1. Then, the second dot is replaced, giving 192.168.1.1. Finally, the third dot is replaced, and we get the fully transformed string 192.168.1.1. This transformed string is the result of the replace operation and represents the defanged IP address. Now that we have the transformed string, the function simply returns it as the output. In the first example, the returned value is 192.168.1.1. Moving on to the second example, the input IP address is 10.0.0.1. Again, we start by initializing the input, where address holds the string 10.0.0.1. The replace operation is then performed using the same method, address.replace. This method works through the string step by step, replacing each dot with dot. After the first replacement, the string becomes 10.0.0.1. The second replacement updates it to 10.0.0.1. Finally, the third replacement results in 10.0.0.1. With the transformation complete, the function returns this new string, which is the defanged version of the original IP address. In the third example, the input IP address is 255.255.255.255. Just like before, we begin by initializing the input string in the variable address, which now holds 255.255.255.255. The replace operation is then applied to transform the string. The replace method scans the string and replaces each dot with dot. After the first replacement, the string becomes 255.255.255.255. The second replacement updates it to 255.255.255.255. Finally, the third replacement produces 255.255.255.255. This transformed string is the defanged version of the input, and it is returned as the final result by the function. The solution consistently applies the same straightforward process to handle any valid IP address string. When analyzing the time complexity of the defanging pattern method, we start by focusing on the length of the input string, denoted as n. The method uses the replace function, which scans the input string one character at a time. For each character, it checks whether it is a dot, and if so, it replaces it with the string. This operation involves two parts: scanning the string and constructing the new string. Scanning the string is a single pass, which is an O-N operation. For the replacements, each dot is substituted with a longer string, dot. And appending this substring takes constant time per operation. Since the output string's length is proportional to n, the process of constructing it also scales linearly. As a result, the overall time complexity of this method is O(n), where n is the length of the input string. Now, let's look at the space complexity of this method. The input string address itself occupies O(n) space since it contains n characters. The output string, which includes the replacements, will have a length of n plus 2k, where k represents the number of dots in the input. In the worst-case scenario, if every character in the input string is it, the output string would grow to 3 times the length of the input, or 3n. However, in big O notation, this is still O(n), because we focus on the dominant term. Additionally, the replace function does not allocate extra memory for intermediate steps, it processes each character in constant space, O(1). Therefore, the total space complexity of the method is O(n), with the memory required for the output string being the dominant contributor. For comparison, a naive approach to solving this problem might involve manually iterating through the input string and appending characters to a result string one by one. For example, you could write a loop that checks for dots and appends either the original character or to a new string. This naive approach, while straightforward, has significant inefficiencies. Although it also traverses the string in O(n) time, the repeated use of the plus equals operator during string concatenation creates a new string in memory for each operation. This means that for a string of length n, the total time complexity becomes O(n) squared, in the worst case. On the other hand, the replace function, as used in the optimized solution, avoids this issue by internally managing memory allocation more efficiently. It performs the same logical operations as the naive approach but ensures that both time and space complexities remain O(n). To better understand this, we can analyze different cases. In the best-case scenario, the input string contains no dots, so no replacements are needed, resulting in a time complexity of O(n) for scanning and a space complexity of O(n) for storing the input. In the average case, with a typical number of dots, the time and space complexities remain O(n), because the operations scale linearly with the input size. Even in the worst-case scenario, where the input consists entirely of dots, the complexities still remain linear, as both the scanning and string manipulation processes scale directly with the input length. Finally, we can confirm these conclusions with a mathematical breakdown. If the input string has n characters and k dots, the replace function examines each character in O(1) time, resulting in a total traversal time of O(n). For each dot, it appends the string dot, which is a constant time operation. Consequently, the overall time is proportional to the input length, making it O(n). On the space side, the output string's length is directly proportional to the input size, as it includes the original characters plus the replacements. This means the space complexity is also O(n). Both the time and space complexities are therefore linear with respect to the length of the input string, making the replace function an efficient and optimized solution for this problem. When working on problems like defanging an IP address, there are some common mistakes you should watch out for. First, be cautious about trying to modify the original string directly. In many programming languages, such as Python and Java, strings are immutable. This means you can't change them in place, and attempting to do so could lead to errors or unintended behavior, like unknowingly creating a new string instance. Instead, it's better to use a new string or a list to handle transformations. Next, avoid inefficient concatenation inside loops. For example, using result plus equals char in a loop creates a new string object every time, which can result in O(n²) time complexity for long strings. A more efficient approach is to collect characters in a list and join them at the end. Additionally, you need to handle edge cases carefully. Scenarios like empty strings, strings without any periods, or strings made up of only periods can easily lead to runtime errors or incorrect results. Lastly, be mindful of how string replacement methods work. For instance, in Python, calling string.replace without assigning the result to a new variable won't change the original string. Many string methods return new instances rather than altering the original, so always ensure you're using the returned value appropriately. Another pitfall to avoid is overcomplicating your solution. While regular expressions or advanced string manipulation techniques might seem appealing, they can make your code harder to read and maintain. Often, a simple iteration will suffice and is a better choice unless performance requirements demand something more sophisticated. Now, from an interview perspective, this problem fits into a broader category of string transformation challenges. Identifying patterns like character replacement, removal, or reordering is a valuable skill to demonstrate. Additionally, efficiency is key. For example, using a list for intermediate storage achieves O(n) time complexity instead of the O(n²) that arises with repeated concatenation. During interviews, it's important to communicate your approach clearly. Explain why you chose a particular method, and if you opt for simplicity, justify it, like mentioning that a brute force approach works well for small inputs. Lastly, don't hesitate to ask clarifying questions. For example, confirm whether the input string could be empty, null, or contain unexpected characters. This will not only help you avoid mistakes but also show the interviewer that you're thorough in your problem-solving process. This type of problem also shares similarities with other string-based challenges, which can help you build transferable skills. For instance, LeetCode 344 involves reversing a string, while LeetCode 151 focuses on reversing the order of words in a string. Problems like LeetCode 271, which deal with encoding and decoding strings, also require careful string manipulation. Exploring these related problems can deepen your understanding of common patterns. Now, in terms of alternative approaches, one straightforward method is to use built-in string functions. For example, in Python, you can simply use string.replace to replace periods with "it" in a single line of code. While this approach is concise and easy to implement, it's less flexible if additional transformations are required, and not all programming languages offer similar methods. Another option is the two-pointer technique. This involves using two pointers to construct the transformed string, either in place, if the string is mutable, or in a new buffer. The two-pointer approach is more efficient for handling large strings but does require a slightly more complex implementation. Finally, you could use regular expressions to solve this problem. With a regex substitution, you can replace all occurrences of periods in the string. While this approach is powerful and can handle more complex scenarios, it's generally overkill for this particular problem. Regular expressions tend to be slower and harder to debug, especially in cases where a simpler solution would suffice. For defanging an IP address, the simplicity of direct iteration or string replacement methods is usually the best choice. Great job on completing the problem. Today, we learned how to solve defanging an IP address efficiently using basic string operations. Remember the importance of edge cases and the versatility of string manipulation in coding. Stay curious, keep practicing, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!